Well, good morning, everyone. As Sal said, my name is Scott Evans, and I'm a research analyst at ARC. This is my first forum, and today I'm here to speak about additive manufacturing, which is popularly referred to as 3D printing. It's been a topic that's been in the news quite recently, and as Sal mentioned, was mentioned by President Obama in the State of the Union address a few nights ago. For today, I'm going to just give an introduction about how the technology works, its applications, advantages, disadvantages, and then finish up with ARC's findings from our first additive manufacturing study. So what exactly is additive manufacturing, and why and or how is it different than 3D printing? Well, short answer is that there really aren't any differences between the two, and the long answer is that many of the differences come in connotation, with 3D printing usually referred to as by hobbyist machines, toys, whereas additive manufacturing is usually referred to more industrial and professional systems. I include a little Google Trends chart, which really just measures the amount of times that people search for 3D printing versus additive manufacturing, and you can see that that 3D printing is much more in kind of the public zeitgeist than additive manufacturing, and that really just underscores one of the big problems of the technology, which is exactly what to call it. There have been a number of names which have been thrown around. I'll read some of them: rapid prototyping, rapid manufacturing, e-manufacturing, direct manufacturing. I wrote down a whole list of a bunch of them, which I'm not going to bother reading, but the point is that there's a lot of confusion on what to actually call this thing. So recently, there's an organization called ASTM International, which is a standards organization, and so they came up with this name, additive manufacturing, and the definition of additive manufacturing is a process of joining materials to make objects from 3D modeled data, usually layer upon layer, as opposed to subtractive manufacturing technologies, such as traditional machining. And this definition has been accepted by all the industry leaders. AMT is one example. So you'll notice that it's a pretty broad definition, and it's really broad for a reason. That's because additive manufacturing really isn't just one technology, but a compendium of multiple technologies, all following this criteria of building thin successive layers on top of preceding layers. So if you want to be really fancy, you might even call it a new philosophy of manufacturing. So in addition to the definition, ASTM came up with 7 additive manufacturing process types. And this was really much needed standardization, because beforehand process types were usually referred to as company brand names, which created a lot of confusion in the industry. Looking at the primary uses for each process type, you can clearly see that the industry is dominated still by prototyping and the creation of castings, molds, dies. And really only 20% of the industry is consumed by the creation of production parts. So I'm going to briefly go through some of these process types. The first one is called material extrusion, which actually functions very similarly to a hot glue gun. You just have a nozzle extruding build material from a filament, and this technology is used more for functional prototypes, testing fin form. Some of the more expensive systems move into production parts. Jigs and fixtures are a focus as well. Material jetting has an inkjet head as well, and it extrudes build material, which is then hardened by a curing lamp, and sometimes in less expensive systems, the droplets just harden by themselves. Material jetting is used to provide visual verification models for the most part, and in addition, some castings. Binder jetting was actually originally called 3D printing, which is another example of the naming confusion in the industry. And this one was spawned at MIT in the mid-1990s. This one is the first powder-based system, and the way it works is you lay powder on a table, and an inkjet head then passes over and deposits adhesive to bind the powder together, and that's how layers are formed. And this is used for visual verification as well, but also can be used for very large castings and molds. Sheet lamination is one of the lesser used technologies. It uses laminates, and it's the first laser-based system I'm going to cover. The laminates are cut into layers by the laser, which is usually a carbon dioxide layer. This one's unique because the build material is usually paper, can even be standard office paper, and it results in a finished product with the consistency of wood almost. And Staples' new 3D printing service, which is recently debuted in Belgium, the Netherlands, uses this technology. That photopolymerization, which is a very unwieldy term in my opinion, is used to provide visual verification and also fit and form models. It's another laser-based system using photopolymers as a material. Power bed fusion is the first technology that I'm covering, which is mainly used for production parts. There are actually a number of technologies producing power bed fusion systems, which is really in contrast to the rest of the industry, as most of the process types are just dominated by one or two companies. It's another powder-based system, and a laser and sometimes even an electron beam passes over the powder, which is laid on a table. And then the powders fuse together to create the layers. And then the final process type is directed energy deposition, which is actually very similar to power bed fusion, except instead the thermal energy is supplied, and also the build material is supplied through a deposition head. So now we have all these methods of building tiny layers on top of each other. So what exactly is this technology good for? Well, first, because all additive manufacturing processes take in data from CAD, whatever can be modeled on CAD for the most part can also be produced using additive manufacturing. Because you're building up rather than taking away, it's a lot easier to create complex designs, internal lattices, honeycomb structures, molds with cooling channels. There's lots of possibilities which are unlocked through additive manufacturing. It's also useful to create lighter parts with similar material properties because you have this advantage of creating, you have an extra advantage of creating internal structures. So I think that this really creates a powerful incentive for innovation, both because some of the previous design restrictions have been unlocked, but also because the cost of producing a failed design is lowered, which is an important part for more risk-averse industries. Secondly, another benefit is material savings, and that's for two reasons. First, because as I mentioned, you can now create designs which utilize materials more efficiently. Second, for most processes, you really only need to use the material needed to build the part. For others, some of the build material not used during one layer can then be reused later in an additional layer. Additive manufacturing, by producing complex parts in one process, can reduce costs and time to market through eliminating assembly times for parts usually produced in multiple steps, and that's another great advantage of additive manufacturing. And now because of the convergence of additive manufacturing and also digital prototyping on CAD, it's now easier to create digital and physical representations of entire systems, and in some cases, just produce the actual system itself. And all these advantages, when combined, can really produce a more efficient and streamlined design process or art-to-part production process. And then lastly, in industries, for spare parts bureaus for industries with parts in circulation for a very long time, additive manufacturing can really just be crucial for reducing inventory holding costs. Because you can more or less produce certain parts on demand and don't have to keep them sitting around for years. So I'll briefly go over what we covered in ARC's first additive manufacturing study. It's actually a very consolidated industry, which is dominated just by a few suppliers. We covered over 25 in total. But a lot of these are very small companies, and as I mentioned before, each process type is more or less dominated just by one company or sometimes two companies. We came up with a market size of over $1 billion. This is just for professional and production systems. We're not including any of the hobbyist 3D printers. While the industry is consolidated in that there are not many large suppliers, there actually are a number of niche players covering different market segments. So it's pretty dispersed in that nature. And the machinery produced is oftentimes very different. And just to give an example, for the range of price and systems, the lower end systems can cost around $5,000, whereas the more expensive systems can cost over $1 million. So there's really a wide disparity in the types of systems in additive manufacturing. And in terms of size, some of them are as small as a normal 2D printer. Most of them are around as large as this podium, and the large ones can be quite as large as a small room even. So in our study, we covered the 7 process types, which I explained earlier, and we also added another process called emerging processes, which is for technologies not yet classified, but ones that we think are going to impact the market in the future. So I'm going to give a brief comparison of our forecasting for additive manufacturing and CNC. Some pretty basic comparison. The two technologies, CNC produces much finer surface finishes than additive manufacturing does. However, additive manufacturing's advantage is that it can create geometries which CNCs can't. So we're really trying to compartmentalize the uses of these for additive manufacturing for small, more complex parts, CNC for larger, less complex parts. So I think that the two technologies can really be complementary in multiple ways. So some of the key industries in additive manufacturing, first is certainly the aerospace and defense industry. There are a number of new design possibilities which can reduce weight for production parts, ducting and prototypes, also expanding into production parts in metal. You heard in one of the speeches yesterday that Airbus is trying to produce an aircraft produced entirely using additive manufacturing by 2050. Whether or not they'll be able to do that is another story, but I believe that they are trying to reduce the weight by 65%, which is quite a lot. In the medical market, hearing aids and dental implants are actually already produced using additive manufacturing. And that's because these must already be customized in order to fit the recipient. For medical implants, the ability to create internal cavities is really important because porous implants allow body tissue to grow in the cavities, which then decreases the chance of the body rejecting it. So that's super important. And then machinery, lastly, additive can definitely play a role in tooling for molds and castings, which can't be produced any other way using traditional machining. So there are actually a number of growth inhibitors for additive manufacturing. In some areas, additive just cannot nor will not compete with traditional manufacturing. Machines are just too slow, and they will not ever be capable of mass producing anything except for items which cannot be produced any other way, and that's where we see the real value added for additive manufacturing. The build trays of these machines are a limited size as well, so with pretty much every build, you have some sort of size-speed trade-off. For each process, there's really a limited number of items you can create using additive before it just becomes more costly than traditional machining. This totally depends on the size of the part, the process you're using, but it's usually in the hundreds, is what we found. Most additive processes produce parts and prototypes which require some finishing afterwards, and that's just because the surface finish really just isn't up to par. There's always some kind of stair-stepping effect because you're building layer upon layer, and I included a picture of that. And so obviously then the parts need some kind of finishing in order to be smooth. When you have a technology designed to eliminate steps in a process and then it creates an additional step through the needing of finishing, then that certainly delegitimizes the justification for any kind of process overhaul. There are a few software limitations as well, and that comes from the fact that CAD just really isn't intended for additive manufacturing. There's a decent amount of work done to export a file to a so-called STL file in order to make it printable. Another problem is that some of these machines come with parameters which need to be acquired, and you need to do additional training in order to make sure that whoever's creating the STL image knows how to utilize these parameters. So actually to address this, the standards organization I referred to earlier, ASTM, is coming up with something called the AMF file format, Additive Manufacturing File Format, which is supposed to encompass some of the intricacies of additive manufacturing, which STL doesn't really cover. and so that should hopefully ameliorate the process to some degree. There are a few limitations in materials as well, and that comes from the fact that these materials are extremely expensive. To give an example, thermoplastics, photopolymers are around $200 per kilogram. That's, can be 100 times more than plastics for injection molding. And then naturally, some of the metal powders for some of the metal powder-based processes are even more expensive than that. And then there are also efforts in order to improve the strength and the surface finish of these materials. One interesting development that we found is definitely in hybrid machines with additive and subtractive elements. One example of this is AG Shamils, which partnered with an additive manufacturing system supplier called EOS, which is based in Germany. They create a process of creating tibial trays, which are used in knee implants. And so the way this worked was that an EOS machine, additive manufacturing machine, constructed the physical tibial implant part, and then it was finished using a 5-axis milling machine, and then an EDM machine produced by AG Shamils. And so I think that really addresses one of the major drawbacks of additive manufacturing, which is that all the parts require some sort of post-production finishing. And so if you try and streamline that process between creating the part using additive and then the finishing of the part, then that somewhat mitigates that inefficiency. Some companies have even gone one step further than that. One example is a company called Matsuura, which is based in Japan. They're traditionally based in machining centers, but they came up with this product called the Lumex Advanced 25, which I've pictured here. And that combines metal powder bed fusion and milling in one envelope. So they're really just including both technologies just in one machine. And so this machine in particular is intended to create molds more efficiently. So Matsuura claims that the molding time is reduced by 33 to 50% in this machine. We think that the development of these hybrid machines could be one really interesting element of additive manufacturing, and yet another example of how machine tools can actually be complementary with additive manufacturing. So what do we expect to happen in the next few years? Well, it's really hard to say because the industry is moving at such a rapid clip. But first of all, I think that we're going to see increased separation and a more pronounced dichotomy between additive manufacturing, with that I mean the more professional and industrial systems, and 3D printing in terms of the hobbyist systems. There's currently kind of like a little blurring of this dichotomy, and a lot of people really aren't even sure what to use what machine for which process. And I think that we'll see this dichotomy become more pronounced as the industry gains legitimacy in the future. Second, we're anticipating continued innovation in these metal-based systems. That's where we see lots of the future, the technology. Faster and more efficient lasers are really the goal of all these companies which are producing laser-based metal systems. I think increasing the productivity of the machines is really going to help cement the business case for additive manufacturing. Production is really key for these machines. I think we're going to see also a gradual price reduction in the materials because they're really just marked up a tremendous amount right now. But on top of that, there's going to be a larger installed base of machines. So I think that the suppliers of additive manufacturing systems are still going to be pretty happy and see a lot of the revenue coming from materials. So we think that the next few years is really going to be the critical point for additive manufacturing. And that's because it's been around long enough to gain some legitimacy now, which you couldn't really say for it a few years ago. But despite that legitimacy, there's also a tremendous amount of untapped demand still. So we see demand really coming from two sources. First is the unfulfilled demand in current form, and that's users who could currently benefit from additive manufacturing but who haven't adopted yet. But second is demand that's going to be created in the future as a result of technological innovation. So either way, it's certainly a very rapidly changing industry, a super exciting one to follow too, and I've really enjoyed keeping tabs on it. As I mentioned or studied before, we also are producing a strategy report for some more specifics on how end users can adopt additive manufacturing. That's all I got. I want to thank you all for your time, and I've really enjoyed this. Mm-hmm. Mm-hmm.